Hi guys, the topic we are going to discuss in this video is XRD. XRD is most commonly known as X-ray powder diffraction technique. The topics which we are going to cover in this video are the introduction of the XRD, generation of X-rays, X-ray tubes, the principle of XRD, X-ray powder diffraction, which is the main technique, the applications, advantages and disadvantages of XRD. So let's get started. X-ray powder diffraction is a rapid analytical technique which can give us a variety of information about the sample, whether it can be a phase identification of a crystalline material, and it can also provide the unit cell dimensions, the crystallite size of the sample, and most importantly, it can tell us whether the sample is amorphous or a crystalline. So, from the data obtained from the XRD, one can clearly identify a material to be crystalline or non-crystalline. The technique was discovered by Max von Lue in 1912, and the basic reason for using X-rays for the diffraction purpose is that the wavelength of the X-ray is of the same order of the interference spacing between the crystal lattices. So, due to this reason, X-rays are preferably used for diffraction purpose. Next, talk about the generation of X-rays, that is, how the X-rays are produced. We already know that the wavelength of the X-rays lies in the range of 0.1 to 100 angstrom. X-rays are produced when electrons with very high speed hit any target material and are thereby rapidly deaccelerated. The target can be any metal, generally a copper target is used, and the kinetic energy is thereby transformed into X-ray radiations. That is E is equal to mv square by 2. Another radiation type, that is the characteristic radiation, is obtained when the electron have very much sufficient energy to remove an electron from its inner orbital. That is, the excited atoms become very much unstable. So, to make it more stable, the electrons from the outer orbital move towards the inner orbital. So, during this process, the change in energy, that is delta E, is gained, and this change in energy is transformed into X-ray radiations, which is named as characteristic radiation. To understand the concept of characteristic lines, we may have to consider the quantum mechanical model having discrete atomic energy levels. So, with the nucleus in the center and the levels, namely K, L, and M shells around it, and by using the formula 2n minus 1 for discrete energy levels, we may have one level in the K shell, 3 level in the L shell, and 5 levels in the M shell. So every transition from an outer to inner shell gives us a characteristic lines. That is, whenever there is a transition from L to K or M to K, then we will get the characteristic. Talking about the nomenclature of the radiation type, the radiation type are divided into two types. If the transition occurs from the neighboring shell, the radiation is said to be alpha radiation, and if the transition occurs from the next shell, the radiation is said to be beta radiation. But the most important radiation which we are going to discuss in the X-ray diffraction are used in X-ray diffraction are the K alpha 1, K alpha 2, and the K beta radiation. But as the energy level difference between the levels in the L shell are very much smaller, so K alpha 1 and K alpha 2 is generally equivalent to K alpha radiation. Similarly, with the case of K beta, and we may write it as K beta instead of K beta 1 and K beta 3. So, we have two types of radiations, K alpha and K beta. But as the electron jumps to the K shell is more likely from the L shell, that is, the tendency for reaching the electron to the K shell is more likely from the L shell as compared to the M shell. So we can say that the intensity of K alpha radiation is very much intense as compared to the intensity of K beta radiation. This is shown in this graph, which we can clearly see that the intensity of K alpha is very high as compared to the intensity of K beta radiations. The presence of two types of radiations may cause some problem in the diffraction pattern. So, in order to avoid this, we may use some filters so that only a monochromatic source with only one radiation type is obtained. So, a filter is so chosen that it may absorb all the K beta radiation and allow to pass all the K alpha radiations through it. The effect of filtration is shown here. That is, before filter, only there are two types of radiations, K alpha and K beta. But applying a filter of nickel, the K beta radiations is absorbed, only radiations of K alpha is obtained. The filter is so chosen that the atomic number of the filter is one less than the atomic number of target. For example, if we are using here the target of copper with atomic number 29, the filter is used here as nickel with atomic number 28. Talking specifically about the X-ray tubes, electrons from the heated cathode are accelerated by high voltage towards the anode. The X-rays from the anode target leave the tube by a window which is normally made up of beryllium. They consist of an evacuated glass envelope which insulates the anode at one end from the cathode at the other end. The cathode is generally made of tungsten filament and the anode is a block of copper containing the desired target metal with a small insert at one end. Now, if we see cross-sectional area of the X-ray tube, the filament is heated by a filament current of about 3 amperes and emits electrons which are rapidly drawn to the target by the high voltage across the tube. Surrounding the filament is a small metal cup which is maintained at a high voltage which is negative in nature as that of the filament. It therefore repels the electron and tends to focus them towards a narrow region called the focal spot. These X-rays are emitted from the focal spot in all directions and escape from the window through two or more windows in the tube housing. Since these windows must be vacuum tight and get highly transparent to the X-rays, they are normally made up of beryllium. The principle of XRD is based on the X-ray diffraction pattern, which is generally denoted by the Bragg's law. It defines the spacing of atomic planes and incident angle at which X-rays of a particular wavelength will reflect in phase. The condition is given by n lambda is equal to 2d sine theta. The X-ray powder diffraction method was devised in 1915 by Debye and Scherer in Germany. After this discovery, it gained widespread popularity because many materials such as polycrystalline wires, sheets, rods, polymeric fibers, etc. may be examined non-destructively without any sample preparation, without any special preparation of the sample. In the diffractometer, the intensity of the diffracted beam is measured directly by electronic X-ray detector. There are many types of X-ray detectors, but they all convert incoming X-rays into pulses of electric current, which are fed into various electronic components, including computers for processing. The electronic counts the number of current pulses per unit of time, and this number is directly proportional to the intensity of the X-ray beam entering the detector. Moving towards the instrumentation part of the XRD, we have the source of X-ray as a sample with sample table C and a detector G. The X-ray source is parallel to the diffractometer axis O, and the source and the detector makes an angle 2 theta with each other, and they both are movable. X-rays diverge from the source and are diffracted by the specimen to form a convergent diffracted beam which comes to focus at the slit F and then enters the detector G. The monochromator or filter, which we have talked already, is placed between the source sample and the detector. It is because it not only suppresses the K-beta radiations but also decreases the background radiations originating in the specimen. We can determine the crystal structure of any sample by using XRD. This process is done in three major steps. The shape and size of the unit cell are deduced from the angular positions of the diffraction lines. First, an assumption is made from the 7 available crystal systems of the unknown structure, and on the basis of this assumption, the correct Miller indices are assigned to each reflection. This step is called the indexing pattern, and once this is done, the shape of the unit cell is known and its size is calculable from the position in Miller indices of the diffraction lines. After that, the number of atoms per unit cell is calculated from the size of the unit cell the chemical composition of the specimen, and the measured density. Finally, the positions of the atoms within the unit cell are calculated from the relative intensities of the diffraction lines. We can also determine the crystallite size of a sample from XRD. This is done by the Schroeder formula, which is given by T is equal to lambda by theta cos theta. It is used to estimate the size of very small crystals from the measured width of the diffraction curves. Here are a number of applications of XRD from which we can identify the various amount of information about the sample. Talking about the advantages of XRD, it is least expensive and most convenient, which can give a variety of information about as compared to other characterization techniques. This technique gives information about the structure of the solids and the arrangement of the atoms of the solid. It permits non-destructive structure analysis. In talking about the disadvantages, it has size limitations, which is much more accurate for measuring large crystalline structure rather than the small ones. X-rays do not interact very strongly with lighter elements, and it is relatively very low in sensitivity. Thank you for watching the video. Hope you have liked this. Don't forget to post your queries in the comment section below.